Average rate of change, average rate of change, average rate of change. That's the same as the slope of the secant line, right? And the way we find it is we set up our difference quotient. So let's go ahead and say A rock, average rate of change. And here's what you show first, right? We're going from x equals 5 to x equals 8. So you'll put f of 8 minus f of 5 all over 8 minus 5. This we're going to check on a quiz that we're having tomorrow. Yeah, this would be the difference quotient. Check, okay? Now, to figure out f of 8, we plug it back in way up here, and we get 16. We plug in a 5, and we get 1. In the bottom, we get 3, so we get 15 thirds, which is also known as 5. And again, notice the notation, bless you, here. We have A rock equals, and once I set up an equal sign, once I set up an equation, I have to keep it an equation all the way through. Yeah. That's f of 8. Convince yourself. Plug an 8 in right there for x.
And what's the point of the A rock part?
Well, we're calling that difference quotient the average rate of change. We're actually just calculating this. See that? We're just calculating. This is from algebra 1, really. It's y sub 2 minus y sub 1 over x sub 2 minus x sub 1. It's just slope. That's all it is. It's the slope. But it's not the slope of a straight line of the curve. It's the slope of the secant line. Okay? And so in this case, it's also the average rate of change. If we graph the function x minus 4 squared, it looks like this, and then it looks like this. And if we look at the interval from 5 to 8 right here, you can see how the graph actually gets from this y value to this y value. It gets there at an increasing rate, right? See how the graph gets steeper? But what we just calculated was the average rate of change, which is this line right here. That line right there, that is called the secant line. And so when we find the slope of that line, we're finding the average rate of change, which is up 5 over 1, up 5 over 1, up 5 over 1, so on and so forth. It's like driving there in your car at a variable speed, that's the bottom one, versus driving there on cruise control, which is the red one. You're going 5 miles per hour the whole time. Whereas someone else that left the same time as you started going 3 miles per hour, but ended up going 8 miles per hour at the end. They're all going to finish at the same time. Okay, so we just call that the A rock, and once we set up the equation, all I'm saying is notationally, we got to make sure that it stays an equation all the way through. There we go. I don't know if that's the right color. Equals, equals. There we go. Now you're welcome to write A rock every time if you want. That's fine too. So the average rate of change is 5. Good. That help?
So like we have 8 and 5, right? And then you're minusing that. Where does that number go then? Does it just go in the denominator?
Yeah. This 8 and this 8 are the same, and this 8 and this 8, 5 and 5 are the same, except the top are the function values. This is y of 8 minus y of 5, and this is x equals 8 and x equals 5. So we have y values and x values, but it's the same. F of 8 minus f of 5 all over 8 minus 5. I don't know if that helps, but look again here. This point right here would be the point 5, f of 5. And this point up here would be the point 8, f of 8. And so if you were to do the y sub 2 minus y sub 1, right, you do y sub 2 minus y sub 1 all over x sub 2 minus x sub 1. And how do we find the f ofs? Well, we plug it into the particular function. In this case, it's the quantity x minus 4 squared. All right, so negative 1 and 9. Again, here's what we would show on a quiz, right? We would say A rock, average rate of change, f of 9 minus f of negative 1 all over 9 minus negative 1. And now that would get a check. And how do we find f of 9? We plug it in. 9 minus 4 is 5. 5 squared is 25. F of negative 1, that gives you negative 5. Negative 5 squared is also 25. And in the bottom, it's over 10. Well, that's 0 over 10, which is 0. So the average rate of change is 0. Now, what would that secant line look like? What kind of straight line? You did it with your hands. Horizontal. Yes, very good. This is a horizontal secant line. So that would be like if you left your house and went to San Antonio for something and then turned right around and came all the way back and got back home to the same place where you left. Your average velocity on that trip would be 0. Did you realize that? Because your displacement is 0. Your starting and ending position are the same. So the displacement is 0 and the average speed is 0. Well, it's all the same thing. Physics is born out of math. Yeah. Yeah. So it's a little bit strange to think about. I drove all the way to San Antonio and back, and I was going like 75, 80 on the highway, right? How can my average speed be 0? Because your displacement is 0. Yeah, very good. So the numerator is like your displacement, yeah, and then the bottom is like your time. So I don't know what y'all call displacement. You can call it x sub f final minus x sub o initial. Speaking of physics, let's look at this. This is an easy one. A pre-calculus textbook is dropped from the top of a tall tower. Who on earth would do that? A frustrated student, for sure. The distance it has fallen after t seconds is given by the function that. Find the book's average speed over the following intervals. Okay, and we'll say that the distance that it has fallen, we'll say in feet. Let's go ahead and give units of feet. So here's what we say. We say the average, you could do this, the average rate of change of height is really equal to the average rate of change, or the average speed, sorry. It's the average speed. Velocity is the change of position, okay? So in this case, we're just going to be looking at the magnitude. So we're looking at the average rate of change of height. We'll call it the average speed. And it's going to be h of 5 minus h of 1 all over 5 minus 1, okay? H of 5 is its final position, its final height. H of 1 is its initial height. And then 5 minus 1, that would be the elapsed time. So how are we going to figure out h of 5? Well, we'll plug it in. So it's going to be 16 times 5 squared is 25. Minus, I plug in a 1, all over 5 minus 1, which is 4. Yikes. How are we going to do 16 times 25? I called it H, sorry. I had tunnel vision. I'm calling it D up above. The distance it is traveled. Guess what 16 times 25 is? If you got 16 quarters, how much money do you have? You have 16 quarters. How much money do you have? Good. You have $4, so that's 400. Guess how tall the tower must have been? The tower was 400 feet tall, because that was how far it had fallen. Assuming it hit the ground at 5, it doesn't really say. It could have been taller. So do we want to simplify this? Is this going to come out to be something nice?
No.
No, not really. By the way, I put D of 1 is 1. D of 1 is actually 16. Did y'all catch that? Okay, that's going to change. Yeah, I caught that just now. Can careless mistakes happen? Absolutely. So this is 16 times 25. I'm going to put this like that so it doesn't look like it's a decimal. Now I don't have to worry about 16 times 25 because doesn't the 4 divide out with the 16 up here? I could factor out a 4 from the top and make that 4 times 25 minus 4. And that's all over 4. And that divides out. Yeah? No, it was 5 squared. 5 squared is 25. We're not squaring the 16. D of 1 is 1 squared, which is 1 times 16. Yeah. So I just factored out the 4 from the 16s. And that just makes it easier because now I get 4 times 25, which is 100. And 100 minus 4 is 96. And this would be what units? Well, here's the nice thing about dimensional analysis. We're measuring the distance in feet. We're measuring the time in seconds. Look at what we get as a unit. Feet per second. Okay? Now, does that mean it was going 96 feet per second the whole time? Heck no. We don't know what it started. It's dropped, so I guess it started off with 0. And if it started at 0, it had to end up going faster than 96, right? By the end? Yep. Sure did. Did it have to be going 96 feet per second at least once, do you think? Yeah, it did. And that's something called the mean value theorem. We'll talk about that in greater detail. All right. We did it for the numbers 1 and 5. Let's do it for the numbers a and a plus h. We're going to say the average speed is going to be d of a plus h minus d of a all over a plus h minus a. Okay, now if I plug in, well, let's not plug in yet. Let's do something in the bottom. D of a plus h minus d of a. And what happens in the bottom down here with the a's? They cancel, right? And we're left with h. Now stare at that expression on the right-hand side there carefully. Do you recognize it? MFP. I don't recognize it. Okay, well, let's keep going until you do recognize it. How am I going to evaluate d of a plus h? I'm going to plug a plus h in for t. So this becomes 16 times a plus h quantity squared. Minus d of a, that's just going to be 16a squared. Wait, what? I'm plugging in an a plus h for t. So instead of 16t squared, it's 16a plus h squared. Now does it look like anything, MFP? Now we expand it out. Square multiply double square, we get 16a squared. Plus multiply and double, you get 2ah times 16 is 32ah. Plus h squared times 16 is 16h squared. Minus 16a squared on the end, all over h. Now does it look like anything like MFP? Still no deja vus? Okay, what happens with your 16a squares? They cancel. Good. And what are we left with in the top? Well, we're left with two terms, both of which that have h. So we'll factor out the h, and that leaves us 32a plus 16h all over h. Now does it look like anything like MFP? Still not ringing a bell? Oh my gosh. What happens with your h's? They divide out, and we're left with 32a plus 16h. This gives us a way to find the average speed now between any 2 points, a and a plus h. Let's try it out on the one before. Okay, if I do this again, and I want to know what the average rate of change is from 1 to 5, that's from a equals 1 to x equals 5. That means a is 1, and how far away is 5 from 1? 4, so h would be 4. I'm verifying what we did over here from 1 to 5. Okay, so that means that I can plug it into there. So we're going to get 32 times a, which is 1, plus 16 times h, which is 4. That's 32 plus 64. That's going to end up being 96. Yeah, it works. And we don't have to set up the difference quotient. We have a formula. That's exactly what we just did. We just created ourselves a formula. If we want to know the average speed of that book, all we need to know is what time and what time interval do you want to elapse. So from 2 seconds, let's let 3 seconds elapse. That would be A equals 2 and H equals 3. And you just plug it into 32A plus 16H and boom, you got it. Isn't it fun to create formulas? What the heck does MFP stand for? I thought you were the acronym age. LOL. OMG, you don't know what it is. ROFTL. SOS. Y'all know that one? Or is that one archived? ROTF. I don't even know what it is. Rolling on the floor, laughing. ROFTL. ROTFL. Okay. BRB. Right. I'm not leaving. I just had to use one of the only other acronyms I know that y'all know. My favorite problem. Does anyone remember my favorite problem? It was the last question on your previous 2 exams. Yeah, that's what we did right here, right? Look at this. This on my favorite problem, I give you this, and I give you this, and I ask you to evaluate. And we've done it so many times, but apparently not enough. So get out a sheet of paper. We're going to drill and kill for the next 3 days over this, right? Until everyone plays it perfectly. I mean, does it perfectly. Yeah. Okay, well, I won't take it personally that y'all don't remember my favorite problem. It was my bad I didn't impress upon you how favorite it was of mine. But one of the main reasons why it is my favorite problem, aside from the wonderful algebra that is involved, right? Every time y'all were seeing that and said, what? What? That's why it's a good problem. But it's also related to physics, which is related to calculus. This problem is related intimately to what we call the derivative. And it's a very important idea. Slope, 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 slope. Slope is a very important thing. Slope is a rate. That's all it is, a rate of change. Like when you buy groceries in the store, $5 per pomegranate. That's a rate. Rates are everywhere. Y'all had like 4 or 5 slope questions on the SAT yesterday, didn't y'all? Or you had to know that it was slope. It said like when x changes by 1 unit, what's the resultant change in y? That's slope. Okay? And it's average rate of change. It could be average velocity, average speed, all that good stuff. Okay, and this, did y'all like my picture of the falling textbook? Thank you. That was very, very hard to find back in the day. It was before Google. I had to use like Alta Vista or web crawler, or maybe it was Yahoo. Maybe, and Yahoo images aren't as good as Bing wasn't around either. So, and then I had to edit it in Microsoft Paint, which is why it's so dang grainy, right? Anyway, there weren't a lot of pictures of the falling textbook. Symmetry. Symmetry is a very, very important thing. Just outside of a math class, we value symmetry as human beings. We think symmetrical things are balanced and beautiful. Our brain wants to naturally reconcile, and so we love symmetry. Our brain loves symmetry. Symmetry is based upon the fact that you can find patterns that are equally distributed. Okay, we as humans have symmetry. We have bilateral symmetry for the most part, straight down from head to toe in the middle, and that's kind of what the first one is. That's y-axis symmetry. A function with y-axis symmetry, like negative x squared or positive x squared, or that graph that we have there, We call them even functions, okay? So with my eyes closed, what's another name for an even function? Or what type of symmetry does an even function have? Y-axis symmetry, yeah. Now there's a test for it. Algebraically is going to be where we're heading, but visually, if you have a graph, it's real easy. The y-axis symmetry is that folding symmetry, bilateral symmetry. If you fold it on the y-axis, does it coincide? Well, the manifestation of that is the fact that if I plug in a positive x, I get out a value called f of x. And if I plug in the negative version of that, I get out, guess what? I get out the same value, which is y. Okay, they're on the same elevation because of the symmetry. So that leads us to this algebraic test, f of negative x equals f of positive x. Okay, and I'll show you how we use that. The other symmetry that we talk about is not it's not x-axis symmetry. It is an odd function. And an odd function, we say, has origin symmetry. They both start with an O, so it makes it easy to remember, right? Origin, odd, odd, origin. Now, what is an origin symmetrical? If you put your finger down here at the origin and you flick this thing like a game spinner, if you let it rotate 180 degrees, it's going to coincide with itself. So this one is rotational symmetry. This value here will rotate all the way around to here. This value here will rotate all the way around to here. This value here rotates all the way around to here, so on and so forth. You could turn your iPad upside down and it looks the same. That's kind of a nice little test. But that's why we call it origin symmetry. You have to put your finger down at the origin. You can't put it somewhere else. Now, there's an algebraic test for this too. If you don't have the graph to visually determine it, okay, here's what it is. Plug in a positive x, and you get out a positive f of x in this case. Plug in a value of x that is the same distance away but on the opposite side, and you get out the opposite value. Oops, sorry, I did that wrong. You just get negative f of negative x. Okay, so what this is opposite inputs give you opposite outputs, and here's the test for that. Opposite inputs give you opposite outputs. So f of negative x is not equal to f of x, it's equal to the opposite of f of x. So that gives us a way to test for odd functions. Now notice the test on both of them involves f of negative x. So here's how we're going to be performing these tests. We're going to replace x with negative x, and we're going to simplify. If it ends up being f of x, we're going to say that it's an even function. If it ends up being negative f of x, we're going to say that it's an odd function. And if it's neither, then we're going to say there's no symmetry. At least not the ones we're looking for. Okay? That's our game plan. Okay, let's try it out. Determine algebraically if the following functions are even, odd, or neither. Verify graphically if possible. Justification. So quiz tomorrow, right? Let's see what would be on it. We're going to replace x with negative x. And to do that, we're going to put parentheses over here where there was an x. And then we're going to drop in the negative x. Negative x here, negative x there. And then we simplify. It's so important that you have parentheses in place when you do these tests because you're going to be replacing things with a negative something. All right, now if I simplify negative x squared, this part here we have to do first. That gives you positive x squared, right? And then positive x squared times the negative makes it negative x squared. And the plus 5 doesn't even have an x to replace. So he's like, hey, what y'all doing over there? Nothing, just come on down. Okay. Now, you compare that simplified to the original. Compare it to the original. Is it the same, opposite, or neither? It's the same. So we're going to put equals f of x. And then we're going to say, so f is what? Even, odd, or neither? Even. Yeah. Now that is the argument. That is the notation that you write to justify whether something is even or odd. Okay? It's something entirely different altogether if you're just wanting to know if it's even or odd and you weren't having to justify it. Because notice there's only one x up here, right? And it's squared. It's an even number. What do we know about raising something to an even power? It's always what? No, it's not what I'm looking for. Because the exponent, it's always positive. Yeah, it's always positive. So a positive squared is positive, and a negative squared is positive. So you can look at it and say, oh, if I plug in a negative x, it's not going to matter because it's an even exponent. It's going to be the same. Therefore, it's even, has y-axis symmetry. Guess why we call these even functions? Because it has something to do with the exponents being even themselves. Yeah? Okay. But the argument, if I asked you to justify, you would have to do this. And I will ask you to justify. All right. Letter B. We got g of x. First step is replace x with negative x. So this is g of negative x. This is going to be a negative x squared minus 4 times the negative x plus 3. Parentheses everywhere there's an x. Okay? All right, now we know that negative x squared is just positive x squared. So that sign did not change, right? Notice the sign did not change. What about negative 4 times negative x? That's positive 4x. Oh, now that sign did change. It went from negative to positive. And the plus 3 didn't even have an x, so it stays the same. Is that the same as what we started with? Is that the opposite of what we started with? No, because to be the opposite of what we started with, all the signs would have to be different. Because that means you could factor it out. So this is not f of x, and it's not negative f of x. So you could just say this is not equal to f of x, nor f or negative f of x. So G has no symmetry. That means it's neither even nor odd. Neither even nor odd. Now, that's the justification. If you just had to look at it to say yes or no, you would look at the first term and say, that's an even function. That's an even number, so no change. Plug in a negative or positive, no change, same. But now we got x to the first, which is an odd degree. Odd degrees are different, right? Because when you raise a positive to an odd degree, it's going to stay positive. And if you plug in a negative and raise it to an odd degree, you're going to get negative. Okay? It keeps the sign of whatever you plugged in. It doesn't nuke it and make it positive. So that one's going to change. And then the plus 3 doesn't change. So here's the deal. To be an even function, when you have a singly defined function like this, an even function is no sign changes. No sign changes. And an odd function is going to be all sign changes. And so if you go through and look at the exponents, you see even, no change, odd, change. That's it. If you get a combination of some changing and some not changing, it's not going to work. That is, if you get a combination of even and odd exponents, it's going to have no symmetry. All right. Now, before we do this one formally, what do you think about this one? Symmetry? Yes or no? Even or odd or neither? Neven? Neither. Very good. The sign in the first term will change. So that one changes. So in order to be odd, we need the second one to change. But the second one is a constant. And by definition, do constants change? No. So this is a change and no change, so this is neither. Now all we got to do is justify it. So here's what it would look like. H of negative x equals 2 times negative x cubed minus 3. That's negative 2x cubed minus 3, which is not equal to h of x, nor negative h of x. So h is neither odd nor even. Something like that. It's not just about being able to determine at a glance. It's about being able to justify. Formulate this argument, okay? Stands up in a court of law. If you should ever find yourself needing this in a courtroom. All right, y'all do this one on your own. Go. I would say try to guess what it is first, and then do the math and justify it. If you think you got it, you can look up. I wrote it up there. So looking at it, you have two variables in two terms. So you're going to be substituting something in. The first exponent is 3, which is an odd number. So that sign will change, yes? The second exponent is implied to be a 1, which is also an odd number. So the sign will change. So we only have two terms, and both signs are going to change. So you should be thinking before you start that it is an odd function. So to prove it, now we do the work. V of negative t is negative 1/2, and then notice parentheses. Parentheses. I plugged in a negative t. It's super important. Super important. Okay. Now when we evaluate it, negative t cubed is negative times t cubed, and that negative times the negative out front make that positive, and here a negative times the negative make a positive. Now when you compare it to the original, it's not v of t, so it can't be even. But if you factor out a negative from both positive terms, which is not what we usually do, but it works, right? Factor out a negative from both terms, and it changes their signs. Verify what I did by going backwards. Take the negative that I have out front and distribute it inside, and you'll see you do get them both to be positive. Okay? Now, that gives me the negative times what I started with. So in the last line, I put negative v of t. And that completes this little sequence. V of negative t equals negative v of t. Therefore, ergo, consequently, or as I like to say, so, v of t is odd, which means it has origin symmetry. You give one or the other. I might ask you to give me the symmetry, or I might have you determine if it's even or odd or neither. Kind of really the same task. All right, any comments or questions? Did we skip it? Oh, good, 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 good. So here's probably what's going to happen. Tomorrow we'll have a little quiz, okay, through this. You can practice this on the worksheet. You'll probably have the limit. I'll ask you if a piecewise function is continuous, where you have to take the limit from the left using one piece, limit from the right, and the function value and compare them. That's from the previous section, like towards the end. Okay? And then we'll get back into the notes. We'll start with number 3, and we won't finish tomorrow then. So we'll have to finish on Monday, and then the worksheet will be Tuesday, and then we'll probably test again. Okay? Because we need to test next week. So this might be the last section before we test. Okay? And then after this section, we're going to jump to exponential functions. So thank you for the reminder about number 3. All right. We actually finished a minute and a half ahead of time instead of going right to the bell. I'm losing my touch here.